Hello and welcome back to Biostats Squid. In this video, we'll cover the basics of MA plots and how to interpret them. So if you're ready, let's dive in. Often when we're doing gene or protein expression analysis, we want to compare two samples or conditions. A great way to visualize your gene or protein expression across two conditions to get an overall understanding of your data is with an MA plot. For example, let's imagine we have two mice RNA-seq samples which have been sequenced. We now want to see whether there are big differences in gene expression and what genes do they affect. And a good start is with an MA plot. An MA plot is basically a scatter plot where each of the dots represents a gene. Let's have a look at the axis now. On the x-axis we have A, or the average log expression across two samples or conditions. So on the right we'll have genes that are highly expressed on average in both samples, and as we move towards the left, towards 0, the average log expression is lower. And by the way, we often use log values as a way to reduce skewness in expression data because expression values span several orders of magnitude, but an MA plot can also be used for other types of data too, which don't need log values. So the x-axis, or A, basically represents the average of your measurements across two conditions. Nice. Now let's have a look at the y-axis. Here M stands for minus because log of A divided by B is the same as log of A minus log of B. A and B would be our condition 1, condition 2. Now, the log ratio indicates how much a gene's expression has changed. You might have heard it as log fold change 2. Let's have a look at some specific examples to understand this better. This blue gene has practically the same average expression in both samples, so we get log 2-fold change of 1, which is 0. So genes that have an M value of around 0 are not really differentially expressed, meaning their values are practically the same in both groups or conditions. What about this orange gene? It's higher in sample 2, so when we calculate our log 2-fold change, we'll have a log value of a high positive number, which will give us a positive M. For example, if the gene has doubled the expression in sample 2 compared to sample 1, the log 2-fold change of 2 will be 1. If the gene has 4 times the expression in sample 2 compared to sample 1, the log 2-fold change of 4 will be 2. So genes with a positive M are upregulated in sample 2 compared to sample 1. And you can follow the same logic for a gene that is higher in sample 1 compared to sample 2. For example, if the gene has half the expression in sample 2 than it does in sample 1, then log 2-fold change of a half will be minus 1. If the expression decreased by a quarter, M will be minus 2. So essentially, downregulated genes in sample 2 compared to sample 1 will have negative M values. Easy. So essentially, MA plots allow us to compare two samples or conditions by visualizing the relationship between the magnitude of measurements and their differences. In other words, we're plotting how much the genes are expressed and how big is the difference in expression between the two samples. Now, in our example, we were comparing two samples, but you could plot an MA plot with multiple samples too, but essentially we want to compare two conditions. The key here is that you're comparing two different conditions, whether that is treated versus untreated samples or two different methods. For example, gene expression values of the same sample sequenced by Oxford Nanopore or PacBio. Great, so let's cover a few tips on interpretation of these plots. MA plots are great to assess overall expression trends. In general, we expect this sort of shape. Low expression genes towards the right show more variability, that is higher and lower Ms, and as we move towards the left, where genes are more highly expressed on average across both conditions, then the variability is lower and there are fewer genes with big differences between conditions. The overall shape of the image plot can already give you clues whether there's something off going on. It helps you see if most genes are unchanged, so points near M of 0, or if there are many genes with large fold changes. It's good for general QC too. For example, after you normalize your expression data, you should see that most of your points are centered around an M of 0, as most genes won't be differentially expressed between conditions. Image plots are also great to check that there is no systematic bias between conditions. In other words, you expect some genes to be upregulated and some to be downregulated in one sample versus another. If all genes seem to be upregulated in one condition and it's not something you expect based on biological differences, then there may be technical biases you need to correct for. Of course, MA plots are also great to spot interesting genes that are very different between conditions and are also very highly expressed. You can add the gene annotation to your plot as well, which we will learn how to do in the next video following an R tutorial, and this can already help you spot some interesting genes. Finally, it's important to know that although we're considering an M higher than 1 or lower than -1 as up or down regulated, this is not a statistical test. Remember that if a gene has an M higher than 1, it means that it's more than double in one condition versus another. But you don't know whether that difference is significant. For that, we would need to use a volcano plot, which I cover in another video, which is a way of visualizing differential gene expression analysis, where there's an actual statistical test telling you whether that gene is significantly differentially expressed or not. A volcano plot will plot the log2 fold change, or M, and the p-value, allowing us to zoom in into specific genes that are significantly differentially expressed. An MA plot, however, isn't associated to any statistical test, so we just get an overall idea of what genes are very highly expressed on average between conditions and also very different between conditions. And that is it for today. Squid-tastic! Hope this was a clear explanation of MA plots and how to interpret them. In the next video, we'll follow an R tutorial to plot our own MA plots in R. Thank you very much for watching and see you in the next one.